Hello, welcome back to 61C. We are starting a new module. This module will deal with pipelining. So far we have designed a functional unit and evaluated its performance, but we really didn't get a sense. Is that performance good or bad? And is that the cycle time the only measure of performance? What we'll do in this unit, we'll actually start measuring the performance, or different ways how we measure the performance, and then figuring out the way how to improve it. So let's get going. In our new school of machine structures, we have looked at different layers of hierarchy and how can they support parallelism. Now we are going to take a look at parallelism at the instruction level and what do we need to do in the hardware, in the execution units, to support simultaneous execution of instructions. We are also introducing one of our 6 great ideas in computer architecture, which is performance measurement and improvement. What we mean by that is we need to know how to measure the performance in order to be able to improve it. So let's get going. We had one measure of performance, which was the minimum cycle time that we needed to execute an instruction in our single cycle RISC-V CPU. And we determined the time by trying to measure the time that it takes to execute each of the 5 phases of execution. So we looked at the instruction fetch and found out the instruction fetch takes 200 picoseconds. That instruction decode takes about 100 picoseconds. The ALU operation that is our execute phase would take another 200 picoseconds. Memory access would take yet another 200 picoseconds, and finally write back would be completed in 100 picoseconds. When you sum all of that up, the minimum cycle time was 800 picoseconds. Now, not every single instruction goes through all 5 phases of execution, and we found out that it was just only one of them, load word, that went through all 5 phases of execution. But we can have a processor that we could possibly think of trying to clock this processor faster, but then it would not be able to do load word instruction, although it would be able to do most of the other instructions. So always our critical path is set by the longest instruction here, the longest time that an instruction takes. In this case, that was 800 picoseconds, and we determined that the maximum clock frequency is equal to 1 over those 800 picoseconds, and that was 1.25 gigahertz. And that was one measure of a performance. So our single cycle CPU can execute instructions at 1.25 gigahertz. That means that it can start an instruction and complete it within 800 picoseconds. And then can start another one that would take also 800 picoseconds, and so on. It would finish 1.25 billion instructions per second. So the question here is, can we do better than that? And is that the only measure of performance? So generally, when we take a look at the spec sheet for any kind of a product, there are usually different kinds of performance measures. So in this case, let's try to see what do we mean by a performance of a processor. In some cases, it may mean that it may have a quicker response time. So if you give it one job, will it finish it sooner? So the time to execute one job may be a performance measure. Or how many jobs can it do in a unit time? So, how many web pages can it serve, or how many spoken words can it recognize, or how many chess games can it do? Can it play in an hour? Or how much energy does it take? Meaning, how long will our battery last when running this processor, running tasks on this processor, like watching movies. How many movies can we watch on a battery charge? What is useful to think of while we are getting a sense for a processor performance, to think of something that is much more familiar, like transportational analogy. And in the transportation, we can take a look at the performance metrics of a sports car versus performance metrics of a bus. And usually people think of a sports car as a performance car. But bus is also a performance vehicle for under certain metrics. So let's take a look at on the left-hand side specs for a sports car and specs for a bus. So the sports car can carry 2 passengers, the bus can carry 50 passengers. A sports car can go at 200 miles per hour and the bus can only go at 50 miles per hour. And the gas mileage for the sports car is 5 miles per gallon, so it can go more miles per gallon than a bus that can only go 2 miles per gallon. So let's see how they perform on a task that involves transporting 100 passengers over a 50-mile trip. And in this case, we're just going to assume that we are measuring only one-way travel, and both the car and the bus immediately somehow come back to the starting point, reload the passengers and go back. So we are just measuring the time that it is taking to transport the passengers. So a sports car will travel 50 miles in 15 minutes. The bus will take an hour. But in every trip, the sports car will only deliver 2 passengers and will somehow transport itself empty and take another 2 passengers. So in total, to transport 100 people will take 750 minutes. On the other hand, the bus will take only 2 trips, so it will be done in 120 minutes. The energy efficiency of a bus is a lot better than the energy efficiency of a car. The car takes 5 gallons per passenger to deliver them 50 miles to a destination that is 50 miles away, and a bus takes only 0.5 gallons per passenger. So we see a difference here in what does it mean something having a higher performance. Yeah, a sports car is better if we have something that is of a very high value that needs to be transported 50 miles away. An injured person, for example. But bus is much better in moving a lot of people over a distance. So it will do it in a much shorter time and save a lot of energy. Let's see how does this relate to the compute performance. So in the transportation, what we had was trip time. In computer world, that metric of performance will be program execution time. How long does it take to execute a program, or for example, time to update the display with a new picture. The second metric that we had was the time in transportation world, time to transport 100 passengers. In the compute world, it is a metric that measures how many tasks can we do in a given time. For example, in this case, it would be how many web pages can be served in a given time, or how many server requests can be performed in an hour. And then the third one is the energy efficiency. The way how we measure the energy efficiency in the cars is, gallons per passenger. In a computer, we also measure energy efficiency by the amount of energy used, electrical energy used. So in this case, we would measure the energy per task, or how much energy does playing a movie take, or how many movies can we watch from a battery charge. Keep in mind that the energy is important for both mobile devices, where we kind of have a better sense for this, how much energy is stored in a battery. Energy is also very important for high-performance servers that live in warehouse computers, in data centers. Over there, the cost of running a data center is essentially the cost of energy. The hardware, the energy cost overshadows the hardware cost after about a year or a year and a half after deployment. So that's a big deal in every application domain or in every domain of computing. Finally, one thing that is important to notice that power is generally not a good measure of efficiency. Energy is much better. Power is a rate of exchange of energy, so they're kind of related. But the way how we can think of it is we can have a really low performance CPU that is very low power, very, very low power. But it would take so long to complete the task that it would basically drain the energy by the time it's done. On the other hand, some better optimized CPU can probably do multiple tasks, long tasks with one battery charge. We'll see a bit more about that later, but for now what we want to remember is we really care about the energy. Energy is what is stored in the battery, and that's what the utility charges us in units for delivering us the energy, not the power. So that's it for the quick introduction. So we are going to try to take a deeper look into the processor performance after a quick break.